Earth's systems generate energy in many different ways, from movement in the atmosphere to the motion of water and the legacy of the diversity of life. "310 million years ago, Kentucky was part of the supercontinent Pangaea and situated near the equator. Stephen Greb of the Kentucky Geologic Survey studies the Appalachian coal deposits to understand how coal is created.
If we look at the topography of eastern Kentucky today, it's characterized by steep-sided hills, deep valleys. The hills are covered by forests, and we live in a seasonal climate. But back 300 million years ago, during the Pennsylvanian period, this would have been a broad, flat landscape, and we would have been under a tropical climate. And in that tropical climate, vast peat swamps were accumulating, and those peat swamps are the coal we use today. What we're looking at here is sedimentary rocks that were laid down as layers millions of years ago. When we get down here at the bottom, we've got a gray shale, and there's actually roots from the wetland plants that lived in this ancient floodplain. Here's a small root right here. This right here is a much larger root. So this may have been to a tree that was like a swamp tree living in the floodplain. When we come up to this stage, it's a much darker colored shale. There's much more carbon being preserved here. And we actually get to where we start to get thin coal beds up into a thicker coal bed. To get coal, peat has to form. To get a peat, you have to accumulate plant debris for a long period of time, and that plant debris and the carbon that's in that plant debris stays there. To get a coal like this, you have to compact the original peat at a ratio of about 10 to 1. So that tells us it was 10 times this thickness 300 million years ago. If we look at the coal and the rocks around it, we commonly find fossils, like this reed-like fossil here. And those plants, when they were alive, were taking in carbon dioxide, giving off oxygen, and they were storing carbon. And that carbon is locked inside this coal. That means that this coal will burn. It's the rock that burns.
Coal is not the only valuable fuel we use today from the hydrocarbon family. Deep on the ocean floor, countless buried microorganisms from Earth's ancient oceans have, over time, created vast pockets of oil and natural gas. The quest for these organic fuels has led geoscientists to many special places as they try to solve the complex riddle of underground oil and gas reservoirs.
4 subsets in it.
The Permian Basin in the Guadalupe Mountains of far west Texas was once the bottom of an ancient ocean. Today, it's one of the most studied marine areas on the planet. Many different types of carbonate rocks form in the oceans. What we know as limestone is one of those. Around the world, there are many oil deposits associated with these carbonate rocks. This area, in particular Shumard Canyon, draws scientists from around the world because here are opportunities to study an ancient oil reserve found nowhere else on the planet.
Another day in the office. The Permian Reef Complex is the outcropping equivalent of some of the larger oil reservoirs in the contiguous North American continent. The unique opportunity here is that in the outcrop we can see the reservoirs completely exposed. We have a complete expanse of rock to look at the different rock types that make up an oil reservoir. Here we have about a 5,000-foot vertical exposure, what would have been a tropical reef system out into a deep water basin, all in a space of about 2 to 3 kilometers.
Charlie Cairns and Jerome Belayan of the Jackson School of Geosciences are no strangers to the Permian Reef. Each trip provides them an unlimited opportunity to literally walk through the history of an ancient ocean.
Well, definitely you can see the sponge spicules in here, which are those nice circular outlines. Typical of the deep water section, but there really are no other indicators. I don't see any trilobite fragments or other things in here. Just in that dark organic content, that's the Darwin thing.
What makes the Permian Reef so extraordinary is that scientists know that what they see exposed here mirrors what can be found elsewhere deep under the ground.
You can walk a timeline from the shelf down through the reef, into the slope, into the basin, and you can basically see all the relationships that you want to understand in the subsurface, and they're all laid out like a map.
One of the most useful tools Kierans and Balayan use to retrieve information locked in the sediment is an instrument known as the LIDAR, short for light detection and ranging.
The unique opportunity with LIDAR system is that it allows us to build a high-resolution digital image of the Earth. And using that digital image of the Earth's surface is basically a very, very high-resolution digital elevation model. The base.
LIDAR works in a similar way to radar, but instead of sound, it sends out light. The change in its property in the time the light takes to travel back creates the data that forms an image. This detailed LIDAR image is created using only 1% of the data that they've collected. LIDAR's measurements are so precise that the vertical measurements are within 6 inches. Because the Permian Basin offers a rare opportunity to study ancient oil reservoirs, the data captured here with the LIDAR is often used to compare with oil-producing formations around the world.
I mean, ultimately, we should get both sides of the canyon going in, and then...
With oil getting harder to find, some scientists are using specialized land-based technology like LIDAR to help locate and define new reservoirs.
Yeah,
Meanwhile, others are launching brand new tools to explore the bottom of the ocean.